So let's have a look uh, on the triangles in one axial compressor, one stage of axial compressor. So as you can see, you have axial direction and tangential direction. Why don't we have radial direction? Because we said that we are assuming that uh, the flow in radial direction is not changing. So this is a simply this is is an assumption that uh, actually makes life easier for us to analyze everything right now. So the flow is two-dimensional right now. And the flow is moving from left to right, as it is indicated in here. So what it first sees is your inlet guide vanes inside your turbo machine. And inside, after passing the inlet guide vanes, the flow actually uh, is guided through this way that we are showing it by v1 vector. So v is our absolute velocity vector. And whatever angle this v is making with your axial direction or z-axis, right? We call it alpha. So v1, this makes alpha 1 angle with axial or z-axis. And after after inlet guide vanes that are like a stator there and they are fixed, you have the first stage rotor blades. And these rotor blades are rotating with some RPM. And this RPM is omega. So at what radius that they are rotating, they are making this peripheral velocity u that is indicated in here. Okay. So you remember from your on physics and uh, previous knowledge, when you have this velocity, peripheral velocity, and when you have your absolute velocity, then it's actually obvious that you have some relative velocity as well, that in this context we are using W for relative velocities. So relative velocity, as you can see, is kind of aligned with your uh, uh, angle of leading edge inside the rotor blade, right? And after the flow passes the rotor, it again comes to the stator blades. And in the stator blades, as you can see, you have again your relative velocity that is decreased. You have your absolute velocity that is increased, and the angle is also increased. And again, you have the same amount of u or peripheral velocity in here. And as you can see, because you have the stator, you are the stator blades are seeing the absolute velocity vector. And on the other hand, in here, we said that rotor blades are seeing the relative velocity vectors, right? So the stators, as it is noted in here, at the inlet and exit of a stator, your absolute velocity is parallel to leading edge or trailing edge angle. And at the inlet and exit of your rotor, your relative velocity is parallel to leading edge and trailing edge angle. So keep this in mind, and then you can just draw these triangles for yourself as well. And again, keep it in mind that what angle is alpha and what angle is beta. So alpha is the angle of the absolute velocity vector, beta is the angle of the uh, relative velocity vector. And then it goes like this. And by the way, you can have some representation of changing of static and total variables during this. And as you can see, throughout the stator part, you don't have, or you have a very small amount of changing of let's say uh, static variables, but the total variables are changing gradually. Okay. By the way, in small engines like microjet engines, as I bring some pictures of it for you, you cannot have axial compressors because the blades will be too small, will become too small, so they cannot compress the gas for you. So that's why in very small engines like microjet engines, you have only radial or centrifugal compressors. And you can see that there could be uh, axial turbines inside these engines as well. So what we understood that the static pressure, temperature, enthalpy, so whatever static variable or property you have, they are increasing inside rotor and stator, but only stagnation properties are increasing and the work is done on the gas. So they only increase inside rotor. So this is the part that we are dealing with, and it is the diffusion. So we said that the area between the blades acts as a diffuser. Why? As you can see in here, when the flow comes inside, it has this much amount of area at the inlet of the passage between two blades. But when it exits this passage, it sees a larger area. So it is like a diffuser in here, as you can see, right? It is like a diffuser. So this the static pressure increases a bit, whether in a rotor or in a stator, due to this diffusion fact. So we said that in a stator you're dealing with the absolute values, absolute velocities, so you're dealing with V, but in rotor you're dealing with W, so it is your relative velocity. But in both cases, because the duct in between two blades is a bit diverging, is the diffusion is happening. So in both cases, your velocity is decreasing. This diffusion is very dangerous because the flow can separate due to adverse pressure gradient, as we said. So you know that when some duct is diverging, the pressure is increasing, and pressure is increasing means that when you are flowing from this way to this way, you have increasing amount of pressure. So it means adverse pressure gradient. And in adverse pressure gradient, you usually end up with separation. When it separates from the blade, you will have a stall. And as we discussed before, when it stalls, you have get into surge. Now, here we're gonna try to express or write our pressure and temperature rises in terms of those velocities and flow angles that we saw in previous slides. So these velocities u, w, and v, and also these alpha and beta angles, we want to actually express the uh, change of pressure and temperature in terms of this, right? So we have peripheral velocity u, r omega. We have absolute, we have relative, we have alpha and beta. So this is a kind of mathematical work from the equation 4 that we ended up last session, you can write that your shaft power over m dot is nothing but the change of your total enthalpy, and your total enthalpy, it is u v theta, difference of u v theta, and we said that u stays the same, and our total enthalpy is a function of temperature, and we know that our tangential velocity is nothing but Vz times tangent of alpha. If you go back to this, whatever velocity you have in this way, theta is obtained by the tangent. So you have this. Then you can end up with this equation. This equation says that difference between temperatures is actually expressed by value of the velocities and angles, right? These are the velocities and angles, only velocities. So from the velocity triangles, you can also check that tangent alpha 1 and tangent beta 1, when they combined, gives you u over vz1, and also it is applied for beta 2 and alpha 2. So the difference between total temperatures is uh, obtained by this formula. There is no need to memorize these formulas, only the way they are obtained is important for us. Now let's try to give some other parameters that are used inside turbo machines. Uh, the loading coefficients, the flow coefficient, what are these? So we are defining the loading coefficient psi as Cp over U squared times T02 minus T01. And if you define this, which is the flow coefficient, as the amount of axial velocity to the amount of peripheral velocity, then you can express your loading coefficient in terms of your flow coefficient using this relation. And in this relation, AVR stands for axial velocity ratio, that is generally equal to 1. And it is exactly, it expresses exactly how much axial velocity is changing through the blade, through one stage of the blades. I mean, when it enters the stage of blade that is rotating or not rotating, and when it exits, how much the axial magnitude is changing. So if you try to write this rise between temperatures and pressures, you will end up with such uh, equations, and in these equations, what you have only the Mach number, and you have only the flow angles, right? Alpha, beta, and Mach numbers. By the way, this Mach subscript B is the Mach number obtained by the peripheral velocity u. But Mach numbers with subscript z are the Mach numbers that are obtained from your axial velocity, and Mach numbers without any subscript, only with numbers, are the ones that are relative Mach numbers. And you also have another definition, that is the degree of reaction. Degree of reaction, we show it by DOR or simply by R, and it is a fraction of a stage pressure rise occurring in the rotor. What does it mean? It means that how much static enthalpy is raised inside rotor comparing to the static enthalpy rise across the whole stage. Okay, so it means that it is the ratio of H2 minus H1 to H3 minus H1. 1, 2, 3 is 1, 2, 3 is actually entrance of rotor, exit of rotor, which is the entrance of a stator, and exit of a stator. 1, 2, 3. Because rotor is rotating, it's better to define rotalpy instead of enthalpy. So what is rotalpy? Rotalpy is actually the enthalpy plus the kinetic energy of relative velocity. And then in rotor, you can write that the rotalpy stays the same. Then the difference between enthalpy is the difference between kinetic energy of your relative velocity. And by the assuming that your velocity at the entrance and exit stays the same, then you can define your degree of reaction using this formula. And if you use the velocity triangles, you can end up with another formula in here. And as I said, these formulas, the way they are obtained is important, but you don't need to memorize these formulas. Just the physical meaning. So if I ask you what is, let's say, degree of reaction, you can say that this is the amount of the static enthalpy increase in rotor to the amount of its increase in the whole stage. That's all. That's it. And if you continue, you can write this degree of reaction and you can simplify it out and then end up with this formula in here. When we are designing a turbo machine, a typical value for degree of reaction is 0.5. What does it mean? It means that half of the enthalpy increase is happening inside rotor and half of it is happening inside the stator if it is 0.5. So if it is like this, if you put 0.5 in here, this 0.5 cancel this one, then you will end up with this one. So your alpha 2 is beta 1 and your alpha 1 is beta 2. And this is called symmetrical blading in turbo machines. So as our design inputs, whatever we have in our design as input, we have the stage loading or loading coefficient psi, we have flow coefficient, and we have degree of reaction. We said that normally we take degree of reaction equal to 0.5 in the preliminary stages of design, and you have a loading coefficient and flow coefficient that are defined by these two, let's say, equations. So as a review, what did we do? We just saw a little bit information about the similarity. We gave a homework about this to you. And then we switched to the axial flow compressors and fans. And the axial flow compressors, we said that there is a major difference between a normal diffuser and a compressor, which is a rotating diffuser. Then we saw the velocity triangles in axial compressors, and we were able to obtain the pressure and temperature rise in terms of those velocities and flow angles. Then we get familiarized with the degree of reaction and also loading coefficient, flow coefficient, and degree of reaction as our compressor design inputs.